Fog computing is a design paradigm that structures a network in such a way that some of the computation is done closer to the IoT device. The biggest advantage to this is the reduced response time for API calls. Fog implementations like the one just briefly described are commonly employed in highly time-sensitive areas such as oil refineries, factories, and hospitals. So how do we implement the fog? The most simple implementation of the fog consists of a layer of nodes that sit physically close to the IoT device. Fog implementations may also be broken up into several layers of aggregation, each layer catering to a specific need. The distance a node is placed from the IoT device depends on the urgency of the task. A node is a device capable of storing, processing, and responding to data obtained from the IoT device. The two most common types of nodes are fog nodes and fog aggregation nodes, the difference being in response time, storage capabilities, and processing power. Fog nodes are employed in the same local area network as an IoT device, thus having the fastest response time. Fog nodes are responsible for processing and responding to queries as fast as possible. Fog aggregation nodes are employed to consolidate data from multiple sources and perform simple analytics. In most cases, a node acts as a proxy between the device and the cloud, communicating to the device only when there are issues. This graphic shows how services running on a node communicate with the device and the cloud. Nodes will respond to devices when they notice any possible issues, otherwise they pass data onto the cloud for further processing and long-term storage. Let's take a look at an example. Imagine we are tasked with implementing connected valves at a highly productive oil refinery. The valves are capable of only transmitting their current pressure and receiving data. They are not capable of performing analysis. In our first design, we host a service on the cloud that receives transmitted data from this valve and responds to the device if any action should be taken. If the valve pressure reaches a certain threshold, a service running on the cloud will direct the valve to shut down, thwarting possible disaster. Let's consider the issue with this implementation. As we are utilizing the public network, we run into a risk of a highly delayed response. A delayed or lost response will allow the pressure to grow unbounded without shutdown, causing possibly enormous amounts of damage to our facility. We must consider building a more dependable system. We now decide to integrate fog computing into our implementation. We move the service off of the cloud and onto a fog node sitting on the same local area network as the device. This gives us sub-second response time and greater resilience, as we are now no longer dependent on the public network. Fog computing facilitates security by keeping data that might only be relevant for processing and not storage inside the local area network. Consider a hospital running analytics on patients. Some of the collected data may only be needed to autonomously adjust the amount of IV a patient is getting and may not need to be transferred to the cloud for historical storage or processing. For similar reasons, the fog also improves the reliability and resilience of the IoT, as we are no longer traversing the public network every time we need to call some application service and expect a response. Fog computing as it stands today has no intention of replacing the cloud for many reasons, like the cost of processing and data storage. The fog cannot compete with the cloud. We will continue to see machine learning and historical data storage taking place on the cloud. The future of fog computing is a cloudy one, because as IoT devices become more powerful, they will be capable of handling their own computations. However, as we described, there will always be a need for faster processing and response time, so it is unlikely that the fog will completely dissipate.